Thanks so much. I'm really excited to be here. Is that loud? No? To talk about some new work I've been doing. I actually was running both models and experiments last night that you're going to see today on the cultural evolution of compositional problem solving. This is joint work with Marcelo Matar, Sam Gershman, and in particular, Fiery Cushman. So I'm going to start with what I hope is an uncontroversial statement. People are wildly compositional. A chef learns to make a roux and then can combine this with cheese and macaroni to make macaroni and cheese, or shrimp and Cajun seasoning to make étouffée. A carpenter learns to make a dovetail joint, and they can use this to combine arbitrarily sized pieces of wood to make either a coffee table or a chest of drawers. And then, of course, there are these explicit symbolic compositional systems, such as natural language, mathematics, and programming languages. And so I think it's safe to say that at this point, in cognitive science, there's a general consensus that a huge part of what makes human thought so powerful is our ability to decompose big problems into smaller problems and to reuse the solutions to those small problems to solve a vast array of different things that we might encounter. In contrast, when we look at AI, especially modern AI based on deep learning, you get a kind of different picture. So in particular, there's been some empirical work in the last decade that is explicitly trying to evaluate the compositional abilities of deep learning systems, and the results are pretty much across the board pretty disappointing. Now, there are AI systems that are compositional, but they tend to fall into three types. So the classical approach was to use an explicit decomposition of the task provided by the human. More recently, people have kind of softened this by instead imposing an inductive bias for some type of compositionality, like based on objects. And most recently, we've seen some exciting work showing that you can extract compositional information from expert demonstrations often provided by a human. So what these all have in common is that the really hard thing about compositionality, the decomposition, the identification of the right building blocks, is not really being done by the network, it's being done for the network. Now, at this point, some of you might be thinking, but wait a minute, there's an AI system I interact with every day that seems extremely compositional, and it doesn't obviously fall into one of those three boxes, so what's going on there? Well, I think this is indeed a new type, but it's still part of the same class, because ChatGPT is trained on the entire internet. Any compositionality that it demonstrates is just a reflection of the compositionality that humans have developed and put on the internet. Now, of course, extracting that compositionality from text is not a trivial problem, but it's much different than the problems that humans face. Or is it? You know, now that I think about it, I was going to say, oh, we don't just get to freeload off of human compositionality systems that have already been developed, but, I didn't invent a roux. I don't think anyone alive discovered roux for themselves. They learned it from someone else. And if you take a modern programming language like Julia, sure, they're official creators, but to say that they invented it is kind of, it's so similar and based on the programming languages that came before it. And so the point I'm getting at here is that most of the compositional systems that we use in our daily lives are not things that we discovered. They're things that we learned from someone else, and that person probably learned them from someone else, who learned it from someone else, who learned it from someone else. And that iterated learning is what we call culture. So the hypothesis we're exploring in this project is that the nature and extent of human compositionality depends critically on our social learning abilities and the cumulative cultural evolution that those abilities enable. OK, so to get a handle on this question, or this idea, we started by trying to get the simplest possible model that captures some essence of compositionality. So our model is a graph. There are these start nodes, and maybe I'll use my mouse here. No, I'm not going to be able to do that. OK, so there's start nodes and goal nodes, and a task is to get from a start to a goal. All the starts are connected to all the goals by a set of edges that we call idiosyncratic solutions. They're idiosyncratic in the sense that each edge only corresponds to exactly one task. It's only useful for that task. We also introduce a set of compositional solutions. And these are compositional because each solution takes two steps. And each of those steps could be used in multiple different tasks. So the key thing that's really nice about this model and makes it so tractable to work with is that each task can be solved in exactly two ways, one idiosyncratic way and one compositional way. Now, importantly, you shouldn't be thinking about these edges as like actions. This isn't like an MDP. Instead, this is a kind of abstract graph, and each of these edges could involve a very complex behavior. And so there's going to be a fair amount of cost involved with sort of figuring out how to execute the edge. OK, so how does the agent work? What I'm showing here is the agent's sort of knowledge state. And it's a graph that only includes the edges that the agent knows how to execute. So right now it's empty because the agent hasn't learned anything. Fortunately, before the agent has to solve their own task, they get to make some observations of previous agents solving tasks. And we simply add those edges to the agent's initial graph. Now, in this case, that information wasn't useful. It doesn't help you solve the current task. And so they have to engage in costly individual learning in order to solve their task. But let's imagine a alternative world in which the agent was observing our agent was observing previous agents that had the same tasks, but were using compositional solutions. So now when we apply the same social learning step, oh, look at that. There's already a solution. There's no need to pay that costly individual learning. So this is basically the key idea that this model, or this part of the model is capturing, is that compositional demonstrations are more useful to a social learner because it allows them to combine pieces from multiple different demonstrations to solve a task that none of their demonstrators solved. So let's make this more quantitative. We can ask, exactly how likely are you to observe a complete solution to your problem, given that you were observing idiosyncratic demonstrators or compositional demonstrators? So we can express this in the model as a function of two variables. T, the number of unique tasks. So if there's 3 starts and goals, that would be 9. And D, the number of demonstrations that you observe. And due to the simplicity of this model, this has an extremely simple, tidy form. But rather than walking you through the derivation, I'm just going to show you a plot. And what we see here is that this definitely doesn't work, does it? Yeah, OK. So the red line's always above or equal to the black line, so compositional information is always better. Looking across the panels, we see that when there are more possible tasks, compositionality is improving upon idiosyncratic more. And with the number of demonstrations, there's kind of something interesting. So obviously, getting more information is always going to be better. But the difference between compositional and idiosyncratic demonstrations initially increases and then falls. And that's because when you get enough information, then you don't actually need the efficiency of compositional learning because you're likely to observe someone who had your exact task. So to zoom in on that, we can plot the difference between these curves, and that's what I'm showing here. And you can really clearly see there's this sort of inverse U-shaped curve where the height is modulated by the task complexity, or the number of tasks. So I want to emphasize that this is special to social learning. So it's a little hard to make these models exactly equivalent, but if you try to set up an individual learning version of this task, where instead of having D demonstrations, you have N trials, one agent, and you see that when you compare the reward of an agent that tries to be compositional versus just only that's the idiosyncratic thing, that they're almost always doing worse if they're compositional. Now, of course, this is specific to this model, and so I don't want to make really general claims here, but it's just showing that in this specific case, we see that compositionality is helping the agent when it's getting social information, but it wouldn't be useful in the individual case. So having characterized the one-step learning, we can now move on to cultural evolution, making it iterative. So imagine that this is like the first generation. They just take some behavior. And now we apply social learning. So the second generation gets to add some edges to its graph. Each of the agents then does individual learning. And the way this works is they just add the minimum number of edges to find a solution. And in the case of ties, we'll cover that later. And then finally, they take the minimum length path given their current knowledge graph. So that behavior becomes the input to the next generation and so on. OK, so the first question we wanted to ask is, like, does compositionality actually evolve through this cultural process. And so I'll show you a bunch of plots like this, where there's generation on the x-axis, and the proportion of an infinite population that is using compositionality, or a compositional solution. Yeah. So what we see is that indeed it does evolve, and it's actually a kind of interesting shape curve where there's this like long period of like very, very slow buildup of compositionality, and it hits some critical point at which it just takes off, and in this case, asymptotes at 100%. So, but I just like picked parameters that made that plot look good, obviously. So we want to sort of generalize that and ask like, well, in what circumstances should we expect that to happen? So we considered 3 possible requirements. First, maybe that learning benefit I was talking about earlier is really critical to driving this effect. And indeed, it is. So here I'm showing that same curve for different numbers of tasks and demonstrations. And it's kind of easier to see this by zooming out and plotting the asymptotic level of compositionality as a function of number of demonstrations and tasks. And hopefully this looks familiar. Indeed, it has a very similar structure to the compositional learning advantage I showed you before. It's basically a nonlinearity, like kind of logistic-like, applied to the curve on the right. And in particular, in the cases where compositionality doesn't provide a learning benefit, it doesn't evolve. So it's essential. Next, we considered that maybe it's important for individuals to frequently innovate compositional solutions in the absence of any relevant social information. So to be concrete, this is the case where you don't know anything useful from social learning, and so the question is, do you just do the idiosyncratic thing, or do you do the compositional thing? And surprisingly, this turns out not to matter very much. So I was showing you a 1 in a million chance of being compositional by accident. You can push that actually arbitrarily low. Obviously, this is an infinite population, and in a finite population, it'll be a little different. But what we see is that it delays compositionality. It extends that like initial slow buildup phase, but it doesn't change the asymptote. And this holds across almost the entire parameter space. OK, so finally, a sort of more subtle point. Maybe it's important that individuals can sort of incrementally innovate within a compositional system. So this is like, I have a library, and I'm able to like write one extra function that allows me to solve my own problem. So maybe that's important. And in the model, this is a case where you have like one of the edges. This is a case where I really wish I had a pointer, but you can see that one of the red edges that's relevant is available, but the other one's not. And so do you either take the idiosyncratic solution, you're sort of ignoring the compositional information, or do you complete that compositional solution? And this matters a lot. In many, many cases, it's basically you don't get any cultural evolution of compositionality when this completion rate isn't fairly high. And the reason for this, intuitively, is that at the beginning, when compositionality is 0, or very near 0, the probability that you see both edges relevant to your task is extremely low. And so you need to have this bootstrapping mechanism where people can kind of add to the compositional system. And I think that's pretty cool, and it's kind of consistent with what we know about how culture works. And I'll just say this kind of interacts in interesting ways with the other parameters, but I don't have time to talk about that. There's a summary. You can just sort of glance at it. I'm not going to bother reading it. OK, so can I show evidence for this? Like, does this actually happen in the real world? So can I show that? And unfortunately, the answer is no, because that would require doing a historical anthropology project that I just don't have the either ability or willingness to conduct. So I did the easy thing, kind of cop out, and ran an iterated learning experiment. So this is just a direct operationalization of our model. So the way this works is you start with some chemical, C, that's your start node. You have some goal chemical, G, I think, and you need to transform C into G somehow. And there's this kind of mysterious machine that has lots of buttons that you have to like figure out exactly what button you need to press to achieve the desired transformation, and that captures the learning cost. And finally, the way we implement social learning is we just, exactly as in the model, we sample solutions from the previous generation of participants and add them to this manual. OK, so to see what this looks like, I can see here that in this case, the manual provides a compositional solution. So I can go C to E and then E to G. or is it? Yeah, it's G. And so you pull the lever, and you have to wait a little bit. So you can imagine that doing this 8 times, potentially, would be really annoying. So people are incentivized to avoid doing that when they can. And there's a fun little completion screen. People really like that parrot. Like 1 in every 12 participants is like, I love the parrot. OK, so does it work? Here I'm plotting model predictions, and these notably look a lot different than the predictions I was showing before, because this is a finite and fairly small population, and we're also accounting for some amount of noise in the participant behavior. We're not assuming they're perfectly rational. And despite the sort of quantitative differences, this qualitative pattern is still here, where there's this non-monotonic effect of the amount of social information you get on compositionality. So far, I've had the opportunity to run 1 chain in each condition. These are extremely expensive experiments, so piloting is kind of tough. The last generation was run last night. And so here's what it looks like. And I would say it's broadly consistent. There's this really weird thing that happened in generation 5 of the 5 demonstrations case, which was just a confluence of crazy factors that I can tell you about later. I don't think it's actually evidence against our theory. It's kind of a fluke. Just to really quickly talk about some ways we're expanding this work. So I should have added labels to this, but here I'm showing we can apply this to, for example, fully connected graphs. And we see that in different populations, the rows, they converge on different compositional systems, which I think is pretty cool. And we're also trying to get this to work in a more rich task based on sort of this like block puzzle where the targets are naturally broken down into compositional elements. OK, so in conclusion, oh, I was supposed to animate. Oh, well. We saw that compositionality boosts social learning by increasing reusability. And as a result, cultural evolution leads to greater compositionality. Importantly, this holds even in a case where individual rational agents wouldn't be compositional. So this does depend on a few things. It strongly depends on the task diversity and demonstration abundance, which govern the learning benefit of compositional information. It weakly depends on individuals being able to complete a partially learned compositional system, sort of extend what they learned from someone else. And it depends hardly at all on the frequency of like pure innovation. So I'm still trying to decide how to interpret this work. And so I'll tell you 2 possible takeaways, and you can choose whichever one you'd prefer. I'll stop there and take questions.
Great, thank you. 2 questions for Fred. So Peter and Anne, you get some good questions coming up. Yeah.
Thank you much. I love your talk. So I wonder about a pyramid scheme. So here, you're not being rewarded for what your ancestors or your successors are doing. But if you did do that reward, would people then demonstrate in a different way? So they would actually say, well, it's actually a good idea for me to create a more compositional solution.
You're imagining like I care about the person who's learning from me.
To be rewarded based on what they do. That's the pyramid
yes,
aspect.
Yes. We've thought about that, and that's I think one of the next steps we want to go to. I think you'd have to have an explicit pedagogy model where you're not just randomly sampling behavior, but you're like deciding what to tell them. And I would expect that you would get much stronger compositionality in that case.
Thanks for the interesting talk. You briefly mentioned the assumption about the cost of learning, but I think there's also a cost of executing actions, and I'm wondering, so you have assumptions in the model there, and I'm wondering if you've explored a bit more this assumption space. My thought is that compositionality is really not dependent on social learning, and so I'm wondering if that's hidden in this cost structure that you've put a little bit in the model.
Yeah, great. So the cultural evolution model is assuming purely rational agents, and so all that matters is like a few differences in cost, and so you can vary whether in the the case where do you complete a compositional solution or not. If you assume that the cost of the compositional solution is less than twice the cost of the idiosyncratic solution, then they complete, and if it's more than twice, then they don't complete. So that kind of thing was explored here. In the individual model, which you might be thinking of also, the way that you get the negative effects of compositionality is you can either do making it harder to discover the compositional solution than the idiosyncratic one, which seems extremely likely to me. And you can also assume that the compositional solutions are slightly less efficient. And so the reason you get this is that if you're not going to do very many tasks or trials, then you're not going to get the payoff of compositionality. But if you're going to do a whole lot of trials, then the inefficiency costs kind of starts to add up. And so there is a sweet spot. And to be honest, I kind of obscured that in the plot. So I admit it. There is a sweet spot, but it's kind of small. And I think a big question is, as you scale up the model to be more realistic, to have huge numbers of tasks, what that's going to look like, and I don't know for sure.